This assessment asks us to calculate the wavelength of light needed to dimerize 1,3-butadiene. Our equation that we'll use is the wavelength of light is equal to Avogadro's number times Planck's constant times the speed of light divided by delta E, where delta E is the energy gap between the HOMO and LUMO of this molecule, the HOMO-LUMO gap for this molecule. So a couple of things we need to know in order to use this equation. The HOMO-LUMO gap for butadiene is 552 kilojoules per mole. And our three constants are Avogadro's number, Planck's constant, and the speed of light. We can plug these values into this equation in order to calculate the wavelength of light that we need. The wavelength of light that we need then is equal to Avogadro's number, 6.02 times 10 to the 23rd per mole, times Planck's constant. Now, Planck's constant is given to us in joule seconds, but our HOMO-LUMO gap is in kilojoules per mole, so we need to use Planck's constant in kilojoules. And so that's a scaling of a factor of 10 to the third. So we'll use 6.626 times 10 to the negative 37th kilojoule seconds. The speed of light is given to us in meters per second, but our wavelength is usually recorded in nanometers. So we need to convert our speed of light into nanometers per second. That's a scaling of a factor of 10 to the 9th. So we use 3 times 10 to the 17th nanometers per second for the speed of light. And all of that will be divided by our delta E, the HOMO-LUMO energy gap, and delta E is equal to 552 kilojoules per mole. When we go through and we calculate this out, the wavelength of light that we need is 217 nanometer light. 217 nanometer light is in the ultraviolet region, so we need some high energy ultraviolet light in order to dimerize 1,3-butadiene.